Hello. Today I would like to present on the topic hierarchical Bayesian inference and take a test case of astrophysics datasets, especially globular clusters, and understand why this pre-processing step of data is important and how it can be used to further optimize different not only statistics models but also machine learning models. So my name is Shantanu C. Parmar. I am a student at Marwadi University in the major Information and Communication Technology. And let's dive deep into the topic that is hierarchical Bayesian inference. And let's first talk about Bayesian inference. So as you might already know, Bayes' theorem is based on finding the probabilistic output or prediction values for a certain prior data and compared to frequency based models or frequential methods, we don't actually uh, take the entire frequency of a certain data set into the input and based on that derive some output. Rather, we find some pattern into the previous data set that becomes our prior, and using that prior as input parameter, we train our current model to further provide output. Now, the Bayesian inference is very important in cases where we have very sparse data sets or the data set is not having any visible or any apparent clusters, and we want to identify patterns which are not easily identified. So, what Bayesian inference does is it takes a certain parameter or actually these parameters, that is the prior distribution and the likelihood, and provides the posterior distribution, that is the maximum chances of a certain new input parameter or new label to arrive at a prediction. Now, what is prior distribution? Prior distribution is just trend over previous data sets of similar nature and over which we have performed the statistical understanding or just found out its statistical distribution, and whichever object has the highest probability from that data set would be passed on to this current model. Likelihood is the estimation of a new point based on the current data set. So things like which data points have a higher frequency in the current data set. In the standard distribution graph, which of them have higher chances of appearing due to the current distribution of the data. So in Bayesian inference, we build upon not only the current input, that's the likelihood, but also we take care of the prior distribution. That gives us the benefit of working on data sets which are sparse because we already know the kind of trends that this sort of data sets go through previous test runs. And based on that, we are able to give a posterior distribution. A posterior distribution is nothing but statistical analysis that provides us with a certain graph of the probability of a particular output versus the range of such outputs. And we usually pick the output which has the highest probability of appearing in the dataset. Let's take a look at what's the other aspect of this topic, that is hierarchical models. Hierarchical models just were built on different sort of techniques, including no pooling and complete pooling methods. In no pooling and complete pooling methods, they are basically feature extraction methods or feature classification methods rather, where we create a hyperparameter based on a few parameters of certain data points. And we do that to reduce the complexity of the data, to reduce its dimensions. Say, for example, you have 1,000 dimensional data and you want to reduce the dimensions, then you would have one hyperparameter that would control the uh, two or three parameters of say 50 of the data points. Then the other 50 would have a different hyperparameter that does the same for them. So we reduce the number of parameters from 10,000 to say around 100 or something. And then what hierarchical model does is that, so let's go from the basics. What just no pooling does is that it makes 10,000 of such hyperparameters, and that way we don't lose any data. But the complexity of the code is increased because we are having so much. such a large feature space, and essentially we did not do any optimization using this. So the other approach is to do complete pooling, and complete pooling is also inefficient in terms that there's only one hyperparameter for all the parameters throughout the data, and that would not, there's no statistical uh, I would say benefit of doing that, because no parameter is going to be able to fit to all the parameters throughout the data set. So it also leads to loss of accuracy, the model being not completely accurate in terms of the output predictions, and there being cost predictions. Also, the full pooling or the complete pooling, uh, I'm sorry, the no pooling would lead to overfitting. So both of these methods were not good. Deriving from that, we came to conclusion that somewhere in between this continuum of no pooling to complete pooling is where we would find optimum output, and statisticians called it partial pooling. Now, the partial pooling, what it does is it creates multiple classes of such feature spaces, and then those classes are then further. So that's the idea of partial pooling. Now, when those features are now once again described by another hyperparameter or a feature, that is where we come towards the topic of hierarchical models, where we have a three-layered or more than three-layered structure, where the hyperparameters are itself themselves tuned by a hyperparameter, a global hyperparameter of them, and that way we are able to better describe the data. We have higher optimization of the entire algorithm, and also we create a relationship between different parameters, which gives us an idea of how well the data points are connected and what features are actually interconnected with each other. Uh, the most I would say frequent use of hierarchical models is done in marketing, where there are multiple factors that might affect the certain share value or a certain finance output. So we have to predict the output based on so many parameters that it is computationally inefficient and sometimes impossible. So hierarchical model, what it does is it reduces this feature space, and based on previous output, we can better understand like which classes are better, and then create better hierarchical models. So this is just a abstraction of the hierarchical model, in terms that it has different levels. There's the data level, so it's the highest level of abstraction. Uh, then there's the parameter level, where we create parameters, spaces, or the classes of parameters. And then there's hyperparameter level, which is like the parameter of this parameters, and that way we create a tiered structure so that we can better control the classification of these data points. It's The whole idea is to reduce the number of features that we have to process. If we are able to find a better relationship between hyperparameter and parameter, then the better accuracy we would have in our output. Uh, yeah, as you can see, like handling missing data, so also the hierarchical Bayesian methods, what they do is they employ the benefits of both of the methods, that is Bayesian inference and hierarchical models. And because hierarchical models, as we have seen, work great on larger data sets, but what if my data set has a lot of parameters, but the actual data points are not so many? Now, a typical hierarchical model will not work very well for that, because there's not enough training data set, as would any other machine learning algorithm. So when we have a less number of data points for our training space, that's when we want to approach Bayesian methods, because Bayesian methods are usually always trained on probabilistic approach, and they keep in mind the trends of previous data sets. So we have higher training space, and can build upon that. Now, what a hierarchical Bayesian method would do typically is that it would take in account the prior distribution. That's the previous. You can call it p theta. That's the probability of a certain output based on the previous model, or the previous run of the model, plus a few features from the previous model. Along with along with that, we take the likelihood. So, for example, if you have a data set of say 3 or 4 data points, and you want to understand what the fifth data point in that feature space might be. Now, what's the maximum distribution, or what's the distribution of the current data set looking like? And based on that, you can infer what's the maximum likelihood of the output class to be. So that's the second feature, the first one being prior data set. Now, when we combine both of this, what we do is we are reducing the variance in the output, and so we get a narrower and narrower feature space range from which we can select the one with the highest probability. And Bayesian inference alone can definitely give you the output for the model, but the variance range there would be very high compared to the combined mixture of hierarchical Bayesian methods, because you are reducing the feature space using hierarchical models, so there's less data to work with, and then you can get better optimized outputs from that less number of parameters or the hyperparameters. And Yeah, that's pretty much the idea of hierarchical Bayesian methods. One of the case studies that is highlighted here is understanding globular clusters, and it is very important to use such methods in astrophysics-based datasets. Not only this one, because generally in astrophysics there's always a lot of noise. There's a lot of deficiency in data because we might not always have the best picture or the best sensor readings or the best interferometer readings for a certain astrophysical event, and that's why models which are better able to work with data that are sparse and do not follow any usual trends are better for astrophysics datasets. So Monte Carlo and such algorithms which are based on Bayesian inference are excellent for using in test cases like this one, where we are identifying the globular clusters and understanding the number of stars or counting the number of stars using this method. We'll go a bit deeper into this in the next videos in the series. We'll also look at how the Bayesian inference models evolved through the earlier forms, which is just the regular vanilla Bayes theorem, to where we are right now, where it's a combination of probabilistic distribution and also the statistics. We'll also take a look at how hierarchical models actually work with real life data, and what's the rate of parameter space reduction that we are doing. And we'll also in one of the videos feature how this whole astrophysics data set has been done. It's actually a research paper, and we'll take a look at what the findings were from that research. So thank you for joining, and I hope that you continue with this series. It has been quite an interesting journey to learn more about this subject, and I hope that you also find it quite intriguing.